So I arrived here in crop production ecology at SLU not too long ago. Arrived around end of April. And before that, I was doing a postdoc at the University of Sydney. And today I want to share with you some of my previous work in quantifying the extensiveness of pesticide contamination. So as we all know, that pesticides are widely used to protect agricultural production. And as of the year 2015 alone, we have consumed over 4 million tons of active ingredient, which is equivalent to about 0.5 kilogram per person per year. And so when we apply these pesticides into the field, these chemicals can move through every environmental compartments, accumulate in soil, leach to surface water, groundwater, and volatilize into the atmosphere. And when they accumulate in the environment, they can cause negative impacts to non-target organisms. And one of the critical problems that we see with pesticide is the loss of pollinators, which are very important to ensure crop production. There are also studies that shows that pesticides can have negative impacts on human health. For example, it may cause disruption to endocrine systems, may lead to cancer, and also may cause neurobehavioral disorders. So recently, there are also studies that shows that prenatal exposure to pesticide may cause a reduction in IQ points of children. And this may have negative impact to our future economy because each IQ point loss can translate into a 2% reduction in lifetime economic productivity. So if we may have a decrease in future economy, then we may also have to expect that the fundings and investment available for research in environmental remediation may also decrease in future. But despite all these potential negative impacts that we know about pesticide use, pesticide contamination is still very much underrepresented in environmental impact analysis. So this figure is an example of footprint analysis for different food products. So when we talk about environmental impacts, we mainly consider greenhouse gas emission, land use, acidification, eutrophication, water use, nitrogen pollution, biodiversity loss, deforestation. And there is no studies that really look into what is the footprint of pesticide contamination. And one of the reasons is that we are lack of information about what are the active ingredients of pesticide use, on what type of crops they are used, where they are used, and what is the amount that are used. So without this information, it is very difficult to associate the contamination that we observe into a certain food product. So one of the first things that we do to fill in this gap is to try to estimate the spatial distribution of pesticide application rates. So we did this by using pesticide use data from USGS, and we use a spatial regression to extrapolate to other regions based on various environmental, socioeconomic, agroeconomic variables. And then we constrain our estimate based on country-specific data from FAO, and we also condition it to information about pesticide bans and the approval of the use of pesticide-resistant GMO crops. We then benchmark our estimates against some national pesticide use database that is publicly available, and also we get some country-specific data from the literature. So basically, out of this work, what we get is the estimates of georeference application rates for 95 different active ingredients. And this database, it covers 10 crop systems, including about 175 individual crops. And it covers a spatial about 170 countries and territories. So using these estimates of pesticide application rate, we then try to assess the global pesticide pollution risk. So the first thing that we did is to calculate the predict the environmental concentration of different active ingredients in soil, groundwater, surface water, and the atmosphere. And we did this by using a spatial explicit environmental model from Trevisan 2009. So this model, it has a explicit accounting for the heterogeneous of soil properties, groundwater characteristics, and also meteorological characteristics such as rainfall, evapotranspiration, and atmospheric temperature. So it also accounts for the difference in physiochemical properties of different active ingredients. So after that, we calculated the predicted no-effect concentration based on the ecotoxicities of the different active ingredients, and we eventually calculate the risk point as the log transform ratio between the environmental concentration and the no-effect concentration. And we take the risk score as the maximum of the risk point among the 4 environmental compartments that we consider. So if a risk point is smaller than 0, it has a negligible risk. And the higher the risk score, the higher the risk. So in this study, we see that about 74% of global agricultural land is at some risk of pesticide pollution, and about 31% is even at a high risk. So looking at the map, what we can see is that the risk is distributed quite heterogeneously. And if we focus into Europe, so Europe is the continent that has the largest agricultural land fraction that is at risk, and about 62% is at high risk. And whereas Asia is the largest land surface area that has the largest land surface area that is at risk and mainly located in China. And because when different active ingredients are present together in the same medium, they can have synergistic negative impacts on non-target organisms. So it is also important for us to know the number of active ingredients posing risk in each of these locations. So we calculated the number of active ingredients posing the risk to the environment. And here we've found that about 64% of global agricultural land is at risk of contamination by more than 1 active ingredient, and about 20% is contaminated by more than 10 active ingredients. And if we look at some hotspots around in China, we may expect to see more than 15 active ingredients in the mixture. Although in these 2 maps that I show just now, the risk looks very extensive globally, but there are some limitations in this study that might cause an underestimation of the risk. So one of them is that in this study, we did not consider legacy pesticides that were banned before 2015. And we also did not consider the risk from the degradation products of pesticides that can be even more persistent or more toxic than the parent molecule. And because this model is a time static model, so we did not consider the accumulation of the pesticide over time. So these limitations can result in underestimation of the risk that we already see that is very extensive. Saying that the model we use in this study is time static, but we are also interested in looking at the time dynamic of pesticide contamination. So we tackle this then by using a time dynamic environmental model. So the model concept of this is that it considers a vertical soil columns with multiple soil layers, that it describes the topsoil down to either the aquifer or the bedrock. And it also allows the input of boundary conditions, for example, solar radiation, rainfall, evapotranspiration, or the application of pesticide and irrigation at any given time point. And in this type of model, it solves mechanistically the water, heat, and gas flow along the soil column. And it also has a mechanistic accounting for biotic and abiotic processes, such as advection and diffusions of chemicals, absorption and desorption, gas and solid dissolution, equilibrium reactions, And also in terms of biotic reactions, it can solve any microbiome mediated processes, for example, biodegradation, and it also accounts for microbes dynamics, so the growth, the mortality, and the necromass turnover. And it also has a microbial response to water and heat stress and other inhibitions. So one of the first work that we, in terms of pesticides, that we apply this type of modeling is to look at the dynamics of glyphosate contamination. And in this work, we use a glyphosate reaction network. So this reaction network is developed by Daniele, one of the PhD students at UCIT before, and he's now in AgWork in Zurich. So he had developed a very comprehensive degradation pathway of glyphosates, from glyphosate breaking down to simple nitrogen and carbon molecules. So generally, glyphosate follows two degradation pathways. So if it follows the pathway on the right, so it gets degraded into sarcosine, which is a carbon source, a non-toxic carbon source for soil microbes. So it is a happy degradation. But if it follows the pathway on the left, it gets degraded into a compound that is called amino methylphosphonic acid, or we call AMPA. And AMPA still carries toxicity, and it has slower degradation rate than glyphosate. So in this work, we are interested in looking at the preferential degradation pathway of glyphosate under different soil and climatic conditions. So we integrate this reaction network into process-based models, and then we duplicate this vertical soil column over a three-dimensional grid, and then we fit the model with different layers of georeference data set on environmental conditions and meteorological characteristics. Then we run the model on a high-performance computing facilities. We do analysis and reassemble the output into maps for analysis. So I show here an example, one of the simulation output from this work. So the panels on your left is the glyphosate concentration in soil, and panel on your right is AMPA concentration. And from top to the bottom are across different soil layers. So one of the key findings that we see here is that a good fraction of glyphosate has turned into AMPA, which is very persistent and accumulated in the environment. And once it started accumulating, it also started leaching downwards to deeper soil, where the biodegradation rate can be even slower. So in this work, what we can see that the problematic molecule may not be glyphosate, may not be the parent compound itself, but it may be the metabolites that would be the substance that is more problematic, that where we have to have a better idea on how to remediate this. And besides glyphosate dynamics, we are also interested in looking at the time dynamics of other other pesticides. So we apply the similar framework onto the other 95 or 92 active ingredients that we have estimated the application rate before. And because we did not have all the reaction networks for all the 95 of them, so in this study, we use a simplified approach. So we use a first order degradation kinetic without tracking the daughter compounds. So in this one, we are interested to looking at what happens in time. So on your left, the panel on your left is the pesticide, the total pesticide residue in the topsoil, and on your right is the leaching rate. So you may not be able to see it very clearly from the residue, because this is the last 10 years of the simulation. What you can see more clearly is the leaching rate. So over time, we can see that there is a seasonality in the leaching rate that depends a lot on the climatic conditions on that particular location. So looking at a long-term analysis, on your left again is the residual. So this is the total residual average in time, and this on your right is the number of days where the concentration existed a threshold of 1 milligram per kilogram of soil. So if we just look at the map, if we see orangey spots over here, we normally see a corresponding orangey spots also on the other maps, but it is not always the case. So if we look at Europe, so Europe in generally has quite orangey color, which is a concentration. So the average concentration in European soil is normally above 1 milligram per kilogram of soil. But if we look at the number of days of existence, it is not always that the soil has an existence of 1 milligram per kilogram. So in a major part of Europe, the number of days of existence is smaller than 6 months. And one of the reasons is that European Union has a stricter pesticide regulation that bans the use of pesticide that has a high persistence. But looking at this map, one may say that, well, that may not be the case, because if you look at North Europe, it's very orangey as compared to other parts of the Europe, and we will expect to have a similar regulation, especially if we look at Germany. So one of the reasons that create these differences is that cooler climate can have a slower degradation rate. So that resulted in the accumulation of the pesticide at a longer time in those places. So this also shows that when we do a laboratory testing at 20 degrees and we see that the chemicals is not persistent, but it's not always the case in every part of the world. So it may be persistent in some particular type of climate or soil conditions. And in adding to the things that I presented so far, so this type of dynamic model can be a useful tool when we want to look at some timescale analysis, for example, in looking at the exposure frequency of pesticide to some non-target organisms. So there could be a lot of potential in using models for risk assessment. So what's next? I would like to wrap up my presentation, putting up a few key points that I think could be interesting area for future research in this pesticide contamination area, and maybe for discussion later as well. So one of the things that I was thinking is that how can we have a systematic record for detailed record of pesticide use data in time and also spatially? Because currently FAO only provide country-specific data of aggregated functional classes. So it would be interesting to set up a way, a homogenized way and systematic way to have pesticide use data records. The second point that I wanted to put forward is that what is actually the impacts of pesticide contamination on agricultural production in the long term. So we already know that pesticide use have created some problems in agriculture, for example, weed resistance and also loss of pollinations. But in some studies recently shows that pesticide residues can have negative impacts on earthworms and also soil microbes that are responsible for nutrient cyclings. So this poses question on whether pesticide residues can eventually affect soil functions that eventually decrease the yield. And finally is what can we do to maintain yields while having a low or no pesticide inputs. And I know that probably there are some experts in sustainable pest management in the audience, so I would like to hear also later on what we can do in better managing pesticide use. And finally, I would like to acknowledge my colleagues that has been providing me consistent support throughout my research career. Thank you.